So let's try an example related to example 1. A transfer characteristic. Transfer characteristic graph of a JFET is given. ID versus VGS. So VGS is 5 minus 5, and this is 12 milliamperes. And this is in volts. The question is to write the characteristic equation for this JFET. For given transfer characteristic, write the equation for ID. So what is the equation for ID? ID is equal IDSS 1 minus VGS over VP squared. So what is IDSS? IDSS is the maximum current when VGS is 0. So when VGS is 0, this is the maximum current we can have. Therefore, IDSS from graph or from curve, IDSS is 12 milliampere. Next, we need VP. VP is equal mod of VGS off. So what is VGS off? That is when the current becomes 0. When the current becomes 0, VGS is 5. Therefore, VP is equal 5. Then we know the equation for ID, that is ID equal, instead of IDSS, that is 12, 1 minus VGS over 5 squared milliampere. Clear? Second example. The current is also given. This is 12 milliamperes. And this is VDS. What can you tell about VGS here? What is VGS in this question? So the question is minimum VDD to put FET into constant current region. they have given VGS of is equal minus 4 volt, and it is given IDSS is 12 milliamperes. Okay, now it is not given. The current is not given. Only this information is given. We have 500 ohm resistor and N-channel JFET. What can you tell about VGS here? Here, VGS is equal to 0. Okay, here VGS is equal to 0. So, when VGS is equal to 0, for what value will this FET come into constant current region? That is only for this maximum current, right? For this maximum current only it comes into saturation region. That is why ID is equal to, therefore, ID is equal to IDSS to put into saturation. To put into saturation. Is that point clear? If I want to bring this into saturation, ID has to be equal to IDSS. So ID is equal 12 milliampere. So now I have found this current. This current has to be 12 milliamperes. And what can you tell about VDS? VDS ID will be equal to IDSS only for ID equal IDSS for VDS equal VP. But VP equal mod of VGS off. Therefore, VP is equal to 4 volt. And VDS is equal to 4 volt. Are these two clear? So this is 0 volt over here. Here it's 4 volt. And here it's VDD. So VDD is equal ID into R plus VDS. From here, if I apply this potential drop, if I'm equating the potential drop, we will have a potential drop here. Okay, that is I into R, and here we will have a potential drop, that is VDS. If I sum up them, that is equal to the potential drop between VDD and this point. So VDD is equal to this amount. So VDD is equal, that is ID 12 milliampere. Resistance is, this is 12 milliampere. Resistance is 0.5 kilo ohm plus VDSS, that is 4 volt. So VDD is equal, if you multiply these two, we get 6 volt plus 4 volt, therefore equal to 10 volt. VDD is equal to plus 10 volt. Is this idea clear? Or should I go through this once again? Getting these informations is important. If you got this information, the final part you can do. Are you clear with this information? How I got these informations? Or shall I go through it once again? Are you clear with that question? Or should I explain? Saja, how about you? Sarah, have you complete copy? Completed, right? Copy. So we can use FET as an amplifier also. So next subtopic, JFET, JFET as an amplifier. So if you look the circuit, it is very similar to the circuit that we had with BJT. Okay. Only difference is in place of BJT, here we have the FET. Other than that, we have those capacitors, resistors, and everything similar. The input is given between these two terminals, and the output is obtained between these two terminals. So just like the BJT, similar to the BJT, FET can be used can be used in three different configurations or three different modes: common source, common drain, or common gate. So here we are using common source. This is common source configuration. This is common source configuration. In BJT we choose R1 and R2 to uh, bias the transistor. But here the purpose of R1 and R2 is different. The purpose of R1 and R2 is to maintain this voltage, always negative. We want to maintain this voltage always negative with respect to the source. Okay. Sorry, R1, R2, and R3 as well. Okay, we use these three resistors. By using these three resistors, we always maintain this value negative. So that is how we have to choose. So, so this voltage remains negative. In that way only we choose R1, R2, and R3. So next point, the resistors, the resistors R1, R2, and R3 are chosen so that the the VGS value always value is always maintained negative, is always maintained negative throughout the operation of the JFET, throughout the operation of the JFET. So if this has to be true, then Vs has to be greater than Vg. Then only VGS will be negative. So we choose R1, R2, R3 so as to keep Vs greater than Vg. The input capacitor C1 and the output capacitor C2, the output capacitor C2 are applied or are used to maintain DC conditions unchanged. DC conditions unchanged. The same thing we discussed in BJT. Okay. While transmitting signal through them. In short, what it says is it blocks DC current and it allows AC current through them. Capacitor C3 maintains DC conditions across R3. Maintains DC condition across R3. So just like the BJT, here also, when we provide an input, so this is the amplifier circuit, when we give an input, let's say we gave an input just like this, and we are going to amplify this positive half. What happens is it gets amplified, but it is inverted. It is amplified but inverted. So this positive half will be in the negative side. It is amplified, but the phase is also changed. Okay, the phase is also changed. So let's see why that is happening. Why when I give a positive, why it gets inverted. So when we give a positive signal, when we have a positive signal entering, the voltage over here, will increase. This voltage will increase. So VGS will decrease. We know that VGS is VG minus VS. VS is same. VS is same. But VGS is maintained negative, right? VGS is maintained negative. VGS is a negative value. For negative value, when we give a positive signal, positive value, the negative value will slightly decrease, right? For example, let's say VGS was negative 3 and our signal is plus 0.2. So now it is negative 0.8. So actually it has decreased. So this has decreased. If this decreases, if VGS decrease, that means there is more space for channel. There is more, the depletion layer gets smaller, therefore there is more place for channel. Then ID current will increase. Okay, this current will increase. If this current increase, this voltage is constant, right? This voltage has to drop. This has to drop. Then only this current can increase. Therefore, if we sum up whatever we discussed now, when you have an increasing voltage, the output voltage will decrease. That is why it turns 180-degree out of phase. Is that clear? Why it turns 180-degree out of phase? The next point, when the input signal is positive, when the input signal is positive, and increasing, positive and increasing, the effective negative voltage, VGS decrease. So the effective negative voltage VGS decrease. Therefore, ID current increases. ID current increases. And VD decrease. And VD decrease. So input current is positive, VD is decreasing. Similarly, When input is negative, when input is negative, magnitude of VD, magnitude negative and decreasing, negative and decreasing, VD increase, VD increase. Therefore, a phase change of 180 degree or pi radian is observed, is observed between, is observed between input and output, input and output, between input and output. Okay, done. Now below that, write a note. So BJT, it works as an amplifier in the active region, but the FET works as an amplifier in the saturation region. BJT works as an amplifier, as an amplifier in active region, in active region, but FET, but FET works as an amplifier, as an amplifier in saturation region, in saturation region. Second, the PN junction, the PN junction between, the PN junction between the gate, between the gate and the source, between the gate and the channel is reverse biased, is reversed bias. Therefore, input resistance, therefore input resistance is very high, is very high in order of, in order of mega ohm, 10 to the power 6 ohms. It is in the order of 10 to the power 6 ohms. So the current drawn, so the current drawn from the signal is low, from the signal is low. is low. Thus, JFET is suitable to amplify, is suitable for amplification of weak signal. Amplification of weak signal. To understand this part, let's use one analogy. Just think about the thermometer. In a thermometer, you want to measure the temperature. Okay, you want to measure the temperature. Let's say the measured temperature is theta 1. Before inserting this temperature, before inserting this thermometer, the temperature was theta 2, theta 1, and this is theta 2. Now here, this is the actual temperature. This is the actual temperature. But for the expansion, uh, this thermometer will absorb energy from the liquid. So this temperature will go down, right? The temperature will go down from theta 1 to theta 2. Now the thermometer will be reading theta 2. Okay. But what's the actual temperature? Actual temperature is theta 1. So if theta 1 is very close to theta 2, then it is a good thermometer. Just like that, now you are going to uh, amplify the signal. From this signal, if the transistor, uses this voltage or uses this signal or draws current from this signal, that means it is using a portion of the signal and then it is amplifying the remaining. Okay, it is amplifying the remaining. But if the transistor uses very less current or it draws a very small current and amplifies, then that amplifier is much better. Okay, did you get that idea clearly? Why JFET is better than BJT? In BJT, it will draw the current into it. It uses a portion of the current. It uses a portion of the signal as the current. But in FET, it doesn't do that. So we can use this one to amplify small signals also. The BJT is not suitable. Okay. So that's all about JFET. In 2019, you have an essay question, part B. Try that question. Okay. So I'll clear this part. So that's all. I'll end the meeting. Assalamu alaikum.